Was the good part.
Yes, so what you just saw was a musical Jugalbandi. For showing up here. This is the third year of Code Jugalbandi. We debuted, me and Ryan doing it, then me and Naresh the next year, and now we are here back again with Morten and myself.
Thank you.
Thank you. So it's been a lot of pleasure doing this, and I must admit that I learned a lot from Morten while Jugalbanding for over a period of 3-4 months. Yeah.
Yeah. First via Skype.
Yeah, through Skype remotely. And so what we're going to present here today is comparison of paradigms. We'll try to render code in different paradigms: functional programming paradigm, object-oriented paradigm, and in array-oriented paradigm, and try to look at how the same problem can be solved and approached. Should we start then? Yeah?
Good idea.
Oh, sorry. So who in the room has, oh, it's pretty small, but do people know FizzBuzz? Anybody doesn't know FizzBuzz in the room?
FizzBuzz?
What's that? Okay, so FizzBuzz is a mathematical game for children, right? So when they learn mathematics tables, they say 1, 2, when they hit multiples of 3, they say what? Fizz. 4, multiples of 5 is buzz, and multiples of 3 and 5 is FizzBuzz, right? So we're going to do this problem in 2 parts.
That sounds pretty difficult. Maybe we should write some code for it.
Okay, let's do it. So I've written this little pre-baked code in Haskell. I'm sure whichever programming paradigm you're coming from, this looks pretty familiar. You will have a lot of if and else checks. So the first check you would want to probably do is, okay, what's the multiple of 3? So you would put a check saying if the number is mod 3 is true, then I would like to spit out fizz. If it's n mod 5, I would like to spit out buzz, and n mod 15, I would like to spit out FizzBuzz. Otherwise, I'm just going to show empty string, right? And I'm just using Haskell here, and to show you, if I come up with a function, can I just get this? Yeah, thank you. So instead of this, I will now write FizzBuzz, and I'll say I want first 20 numbers. Now I get FizzBuzz with strings, but we said we want, wherever there are empty strings, we want to show the index.
Oh, we missed that in the intro. That's the second part of the puzzle.
Yes.
Right? The first part is just to produce the strings with empties.
Correct.
The second, including the numbers.
Yes. So I will just now do a show of n. In other words, this is converting an integer to a string in Haskell. And this is where I get 1, 2, FizzBuzz. So I'm sure this code looks quite familiar to a programmer coming even to a functional programming paradigm from imperative side, and there's nothing great about it, right? All if and else checks, the control structure is quite visible. You think you can reason about this code very easily, yeah?
Yeah, and the 15 needs to be before the others, right? Because
yes,
otherwise you'll get fizz.
So
yeah.
that knowledge is embedded in the flow here, right? So do you want to show how this looks in APL?
Now, as they say, for something completely different. Is it loaded? No. Yeah. Sorry, I need my glasses. Okay, FizzBuzz. So I'm typing into the REPL here, but I have pre-prepared all of the statements. Now, the way this feels to me as an array programmer, the first part where we don't have to put the numbers in, is I just want to produce 2 cycles of blank blank fizz and blank 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 buzz, and then join them together. So here's a 2-element array in APL. an empty character vector and one containing fizz. If I do the -3 take of that, it says take 3 starting from the right, and I get an extra empty at the beginning. If I then say do the 20 reshape of that, it reshapes that 3-element vector until I have 20 items. So the way I read that, I say the 20 reshape of the -3 take of quote quote and fizz. So for the buzz case, I'm just going to do the -5 take and with buzz. So now I have these two 20-element vectors. And the final piece is just to do a catenate each that I've put in the middle there, the comma and the 2 clause. That's catenate each. And that solved the problem for the first case, essentially without writing any code, but I'll turn it into a lambda just so that it looks like a program. So by putting curly braces around it and then replacing the 20s by omega, which is a reference to the right argument, I now have a function that I can apply with the right argument of 20.
So I see that you're kind of playing here with the shape of the, you've arranged the text in such a way, the array items in such a way that the shape is visible to you. I mean, at every 3rd position you have fizz, at every 5th position there you have buzz, and then you're kind of repeating and cycling through.
Yeah, okay. Just catenating them together. Almost, without programming. There's no control flow here. It's just creating arrays and then
that's important. Yeah.
Now, although in your case it was a natural first step, the case 1 where you don't produce the number. For an array programmer, it really feels more natural if you're going to have the numbers in the result to start with an array of the numbers from 1 to 20. And then selectively replace some of them with FizzBuzz, rather than having that in the code that generates the cycle. So I'm going to do some math on this. The 3 residue, the modulus 3 of those inputs, so we can start to see where they're divisible by 3, or there's a remainder. The same with 5. Of course, I'd rather do those 2 in a single step, so I do the 3, 5 outer residue with my 20-element array. Now, of course, what I really want to know is where are they divisible, and that's where that previous array we computed is equal to 0. So 0 equal to the 5, 3 residue. Now you'll notice I reordered them from 3, 5 to 5, 3. The reason for that is I'm now going to interpret each column of that matrix as a base 2 number using this base value function in APL. So the 2 base value 110, originally implemented in APL as the value of the coefficients, of a polynomial with these coefficients, but of course that is the same as digits in a particular base. So I now have this variable called case, which I have named case, and the quad gets there at the end is just because an assignment would be silent normally, but the quad gets forces it to be output to the session. Now, I'm interested in the ones where it's not 0, so I can say case without 0. That gives me a vector without the zeros in. And then I now need to use that to select from these possible words that I want to merge into the input. And I can simply index. In APL, you can index with an array, which uses the array items one by one to pick from the thing that's being indexed. So this gives me all of the words that I need to merge in. And in fact, there's a merge operator in APL where I can say the words at, and then the right operand to this merge operation in this case is a function which returns a true or false, a Boolean array of the same length as the input. And that merges those letters in at the points where this predicate is true. So that solves the problem. Typically in APL, what you would do is you'd sit around playing with the data. It's very valuable to be able to see it as you play with it, and different solutions are suggested to you. If you collected, then you went back into the log, copied lines out of it into a function. This would be the function definition for FizzBuzz in APL. So 4 lines of code. I start by creating these 2 constants, the primes, the texts, and then we have the computation of the case using base value and the merging of the indexed texts at the positions. And there's no control flow. I would say, it's all data driven. The structure of the APL arrays is driving the application of these primitive functions.
Yes. I think let me...
I think you could do something a bit more like that.
Let me give it a go. Yeah. In Haskell again, I'll stick to Haskell for now. So I'm going to get rid of... sorry, no, okay.
These old men doing presentations.
I'm going to get rid of all this control flow, yeah, and try to look at, is it visible there? Or
it's a bit small.
it's better? Yeah. Okay. So what I'm going to do is now get rid of this, yeah. And so in Haskell, I need to prearrange data like how you did. So I'm going to, so the first thing I'm going to do is prearrange data like this. And this is fizz, and I need to generate a sequence and a stream. So I'm going to use a cycle function in Haskell, which is going to give me a stream, continuous stream of fizzes like this. But notice I just don't need an infinite stream, so I'm going to say take n of that. So yes. So I got fizzes. Okay. So this is, I'm going to extract this into a variable here and call it threes, and just say where.
But that's a lazy thing, right? The cycle is not a 3-element vector as mine.
No, this is a lazy list. All Haskell, the Haskell list is lazy by default. And so this is threes. In a similar way, what I'm going to do now is create fives. Okay. So instead of fizz, now what I'm going to have is buzz. And just going to test this and say fives. Oops. So now I got buzzes at this position. Now I have those threes and fives like what you did. Now I need to zip the two streams up to be able to produce FizzBuzz. Yeah. So what I'm going to do is I'm going to say result is, and in Haskell we have this zip width function, which takes in a operator, binary, because now I'm going to pass into this zip two streams, okay? And this particular function, which is in its curried form here, will take in element by element, and
this is almost identical to my catenate each. Except it's not infix, and it's working on two lazy structures.
Absolutely, absolutely. In your case, you had laid out memory up front, whereas here it's lazy. But yes, this is one level of.
Oh, we have a question.
Yes.
What if you change the 3 and 5 to something else?
We'll get to that.
So.
Good question.
We'll answer it, yes. So now, this is where I could get to. Now, I need a third stream for index, right? So I'll create indices is going to be map of show to from 1 to n. So now that I have indices, I'm going to plug that third stream in here. But notice, I can't use zip width because it just works on 2 streams. So I need zip width 3, which works on 3 streams. And again, you may have a question. I said, what about zip width 4? So this is.
How high does it go? 4, 5, 6?
I don't know. I need to check. But yeah, so that's certainly there. Now this operator also would not support. So I need to plug in a lambda with 3s, 5s, and the index. And now I need to write some structure, because if the 3s are empty and the 5s are empty, then I need to show I, else I will simply go back and concatenate the 2. So now I got this, and this is one way in which I can be data driven in Haskell.
Right, that's very nice. But maybe.
Yes.
Sorry? Yeah, and is it my turn now?
Yeah, well, I need to just show one more. Yes,
right,
I agree. This is as far as I can go, but I could then use Haskell array library and then be exactly like but then I'm falling back on a library.
Yes, then you have to consider all the code from the library.
We'll
Yeah.
return to APL in a moment and take a look at this.
So I will just then, this is the other version of this, since we are running out of time already. What I've done is, instead of hard coding strings like this, I have demarcated like what exactly you did.
Yeah.
Wherever this is fizz, it's demarcated by 1. Wherever there is buzz, it's demarcated by 1. Then I have a text containing the stuff, and the base2 function, Haskell digits library does have undigits2, which is base2 coefficient. And then I do the zip3, and then again, wherever there is index is 0, I get, show the index. Wherever this base2 applying application results in 0, that means I have to show the I, and otherwise I index into this with the bang bang operator.
Would that undigits be useful for evaluating polynomials, do you think?
Yes.
Should have a different name then, though, shouldn't it?
Well, so, yeah.
Right. So in APL, because it's all array-oriented, I think it's easier to be. I forgot these. So I forgot the last steps of my previous section, just showing the application also not just to 20, but to any array. And we've talked about that. Now, so here's the answer to that question. What if you had different primes, or indeed more primes? Well, in the APL solution, all you'd need to do was change those data structures. So 3 here, I now need 2 to the 8th different combinations of strings, but the last 2 lines are unchanged because I'm just interpreting base2. Each column, there are now 3 rows, and the rest of it is unchanged. And I don't have time, fortunately, I don't have time to explain this next expression. But what it does is, given an array of 3 elements, it generates all the 3 combinations. So I could cut this down to just having FizzBuzz bleep and a little bit of code, and then it would be. So, sorry?
Is that code doing an LCM? These common multiples?
No, it's just catenating them, catenating the combinations together. Yeah. So what it's doing is no, let's not get into that. We don't have time.
So I think if we reflect back, based on our whatever we saw here, I think it is important to realize that wherever, if we can possibly encode the program logic into data rather than into control flow, because if you see the Haskell code here, I think it's much easier to look at this simplicity rather than look at the bunch of if-else statements, because the pattern is visible to you right up front. I mean, if I were to do 3, 5s, and 7s, I would have to probably rewrite this, but yeah.
And I mean, one of the differences is, what does the language encourage you to do, right? Yes, you could solve this in a similar way. And in fact, that might be a good reason to learn APL, even if your deployment stack makes it impossible for you to use it. Use APL during the design phase, go back and write something in Haskell.
So that was our...
Or assembler, why not?
So that was our first melody, FizzBuzz. So we're trying to delineate the two, control flow and data-driven, by actually showing examples. Should we move on to the next melody?
I think we should.
And this time I have a melody which is a famous interview problem. I won't name the company, but everybody knows, can take a guess. It's a Mars rover problem, right? A rover has landed onto Mars on a curiously rectangular plateau. Mars is...
With little blue lines on it.
Yes, and it's a grid. It's landed on 2-3 east, yeah? And the Earth station sends commands like left, right, and move forward to the rover. So move forward causes rover to move one grid step in the direction in which it's already headed, bearing. So it maintains the bearings. A left causes the rover to turn 90 degrees left from its position, on its position. And so it's essentially rotate left and rotate right.
Right. So this looks like an object to me with some 3 items of state.
Yes, it's perfect for a rover to carry the state and maintain its state, and then upon receiving each command, respond to the and arrive at a new state. Yeah, mutate the state exactly. Yeah. So let's see how I'm going to take over. Use JavaScript this time. Yeah, because JavaScript also provides object-oriented way of doing things. But yeah, well, so typically an object-oriented programmer would start like this: create a shell for Mars rover. Constructor takes in x, y, and direction. And right now, what you're seeing here is a rove implementation with just a simple two-string method. Rove implementation takes in a command, but just returns the rover itself. So essentially, this code is just sitting there. It's not doing anything, right? So as you start, as an object-oriented programmer starts developing the commands for move, right, left, this looks quite familiar, right? This is what happens. And to an object-oriented programmer, switch case is a smell, yeah? And so one tries to refactor away. Yeah. No.
Yeah, sorry.
Yeah.
I'm sorry. I apologize for my behavior.
This is so this is a smell, and they try to refactor. We try to refactor. Also, if you notice here, x, y, and direction are treated together. So these three variables. So this smell is typically called as primitive obsession in object-oriented sense, and so this we are. So the idea is, how can I find an abstraction on which I can bind these and discover the behaviors on this, right? So the next level of refactoring would be something like this. So the physics vector, from physics you can pull in the vector abstraction, which kind of takes in the direction, and then you shove in the entire switch case logic, and you use a map structure to disintegrate the switch case form into tabular form. So essentially, or if you are using language like Java or C#, you would probably resort to polymorphism. But I think at the end of the day, underlying polymorphism is also implemented using tables. So why not use tables to simplify it? Yeah.
Yep.
So this is what the code will look like. And finally,
there's some significant repetition of code there. Right?
Yes, there is significant,
Still
but the rover works. Yeah, so now, yeah, this is normally the argument presented, yeah?
Yes.
So I'm just saying that.
Yeah.
So now, let's give it a go second time at Mars rover, but this time functionally, putting the functional lens, yeah?
Mm-hmm.
And how would this be approached? So I'm going to steal this particular repetitious data structure.
Those lambdas look very similar.
Okay, so I am going to paste this here, yeah, and I'm again going to look at some real-world object, like what this really means. So I'm going to. So the closest object that comes to me is a compass, right? So compass has all these directions, and but usually if you look at the compass, it has degrees associated with it. So, for example, so I'll just increase the font a bit. In the compass, north is associated with 0 degrees, east is associated with 90, but for the sake of brevity, I will just say 9, because I'll drop the zeros because they have no use anyway.
Saving paint like they do on runways.
Exactly, saving paint. So runway 927 means a east-west runway, aligned runway. So this is 270 for west, yeah? Now I need to get rid of all this duplication which you complained about, right? So this goes out, this goes out, and I can't obviously use x and y because the lambda is gone, so this essentially has to become a 0. This 1, 1, 0, minus 1, 0, minus 1, 0. And let's not call this directions because we have a metaphor here. We have a, let's call it compass. And what I'm going to do in JavaScript, it allows me to at the same time, I'm going to wrap this in a tuple like this. So this is an array. In JavaScript, it allows me to take this array of tuples, and I'll use map.
Okay.
Oh, sorry. Yeah, thank you. Oops. That's 1, so I need to treat this as a whole array, and I should get all the 4 elements. So this is how a JavaScript map looks like. So I have now, in other words, what I've done is I've mapped a tuple north 0 degrees to a movement.
Yep.
Yeah. So so a functional programmer would probably start with a data structure. Now, I've used const here, though the map by itself is mutable, but at least the reference compass is immutable. So this is what I can see best available right now, given out-of-box ES6. So that's what I've done here. And then a functional programmer would start working on the row function, which would operate on this. So a row function takes in x, y, and z as a tuple, yeah, and the command. Upon getting the command, queries the array, gets the keys, and tries to find the exact matching direction, because we notice everything is direction based.
Yep.
So I get east and 9, so which is correct, right? So I'll move on here, where the next step would be to convert this direction into some action, because that's what, based on the command, I need action. So at this point, this is the piece that we need to focus on. Again, I'll query the compass, get the movements which are possible in the for the representative for the east direction. Once I get the movements, I'm using, of course, the array destructuring of ES6 here, and just doing it, and then again querying the commands. So I have also, what I've additionally evolved is another structure here called commands, which is essentially a map. It's a map of lambdas. It's an action map. That's what I'm calling it, because the command is mapped to an action. So whatever delta x and delta y that I give, for example, for left, there is no movement, because a rotation causes no movement. So don't move.
Yeah.
However, when you are turning left, essentially you are turning anti-clockwise. So do a -9, because all our degrees are separated by 9.
Okay.
And then +9 for right. That's the dual of it. And then finally, nothing, no rotation for move, but just simply move. Yeah. So that is 439. But this output is not user consumable.
Well, the 9 is a bit weird.
For pilots, yes. The gliders like you, yes.
For pilots, yeah.
But
so what are you going to do about that?
I need to reconvert this into east, because 9 is east. Yeah. So I again consult my compass and get east. And notice what I'm doing is I'm now giving here a series of commands at the bottom, giving the starting position and doing a reduce over the commands to get the final bearing.
Yeah, I think I understood all of that.
How does that look in the...
Oh, it's going to be a bit different.
Okay.
There's going to be some code, but there's going to be hopefully no abstraction, because I'm allergic to abstraction.
This is basically interplanetary logo.
So first I want to get rid of everything that's up there. So I generate a 20 by 0 matrix, and everything scrolls off the screen.
That's clear screen in APL?
Clear screen in APL.
Wow, I like that.
Okay, for me it's like I don't think we even need those 90-degree things, because it's just 4 directions. They're in a clockwise sequence. So I think we can also do away with that part of it. So I'm just going to create these 2 arrays, a character vector, northeast, southwest, and then a 4 by 2 matrix with those movement vectors. I've catenated them together here. The comma means take the vector and catenate it to the matrix, and that just gives me a 3-column matrix, so I can see what I've done. The initial position, the initial heading, so this is an index into the directions. East is where we start. So now we need to start thinking about, so how do we compute the rotations? Well, these are not the commands in the task. This is just a random set of commands I typed in. If I look them up in the 3-element vector LMR, left, move, right, I get 2 for right because it's at index 2, 1 for move, and 0 for left. If I subtract 1 from that, I get 1s for right, 0 for moves, and negative 1s for left. And those are in fact the changes in the index that I need for each one of the commands. A move is going to make no change, left is going to reduce by 1. So if I have an initial position like west, which would be 3, I catenate that to the front of this list of deltas, and I do a plus scan. Oops. Okay, I managed to do 2 things at once there. If I did apply, I was supposed to do just a plus scan here. So then I get indices resulting after each movement, but as you can see, they go to 4 and negative numbers which are out of bounds. So that's why we need the 4 modulus, just like you needed your 36 modulus.
Yep.
So that allows us to compute the indices into the direction following each command. So if we now take the set of commands that were in the task, I compute a variable which I call bearings and output to the session, which is the bearing following the execution by the robot of each one of these commands. If I index into the movement matrix, I'll get a row of movement for each one of these bearings. So that gives me an n by 2 matrix. And then I catenate, again, the commands on the front of that, just so we can see which of the commands corresponds to each one of these movements.
But I noticed there in R or L, you still have the movement.
Right, yeah. So for R, we wouldn't want to make a move, and we wouldn't want to make a move for L as well. But that's just the heading that the robot has at that point. Fortunately, there's a straightforward solution to that. If I compute this variable called movements, and catenate again, you see I've managed to eliminate the movements for my turns. And I did that by multiplying this matrix with the result of comparing commands to M. So command equals M gives me a Boolean mask with a 1 where there's an M and a 0 for everything else. And then the multiply axis 1 says take that vector, align it with the matrix on the left, and multiply each row with one of these. So that allows me to mask out the movements that I don't want. So if we catenate the original position to the top of this array of the actual movements, and we then do a plus scan. So I'm doing a plus scan here, which gives me the intermediate sum all the way down through this. And then I've catenated the commands on the front again, just so we can see what's happening, and a star for the initial position. Otherwise, we couldn't catenate them, we'd get a length error. We can see the position that the bot has after each command.
You got audit trail for free, huh?
So you see for an R, there was no movement from the previous one. Now, what the task asks us to do is simply the plus reduction. We don't care about the audit trail. That was just so I could satisfy myself while experimenting that the right thing was happening. And then the other thing, sorry, hit the wrong key. The other thing we're supposed to return is the final orientation of the robot, -1 take bearings, which as you had to do, we need to translate back into human speak. So again, after playing around a bit like this, I would collect that into a function, rove, and unfortunately we've increased the font size so the comments have wrapped around, but you should recognize all of the various steps that I took there. I deconstruct the right argument, which has 3 elements. We call it with a 3-element list. So deconstruct that and then go through the steps that we stepped through a moment ago.
So
it's a vegetarian language. Should be good for India.
So I see, like you see, we started from object-oriented solution where we had a vector abstraction, and then slowly as we approached the functional programming paradigm. So in object-oriented paradigm, one trusts encapsulation to do the right thing. That's the trust. whereas in functional programming, the trust is via, the data is out there in open, but it's immutable. So there is this implicit trust in the data. I mean, there is this explicit trust in data because nothing data is not going to change. So the clarity started emerging, but now when I look at this, you have data structure out there open.
That's true. And I mean, I have some big advantages from that. For example, if I decided, as I did when we were playing with this originally, I thought, well, it would be nice to visualize what's happening here, right? Use that audit trail for something. So it turns out this expression, which says, put a star or merge a star at, and here's that audit trail, right? Here are all the sum scan of the positions. I split that, think of this down arrow like an axe going into the array, splitting it into two tuples, and say star at all of the positions visited in the 10 by 10 reshape of this box drawing character, which gives me a grid. Okay, the grid lines are in the middle of the cells. It's not perfect. But it's not quite right because the robot starts at 3.3 and ends at 6.0 on the, so this thing is all. And what you do in APL, then maybe you can't quite visualize which function you need, but you mess around, you type a few symbols, and you find out that it's the reverse on the first dimension of the transpose that you need because the compass coordinates are reversed relative to matrix indices, and row indices increase going down when in fact the robot north is up.
So I see a lot of work in terms of if this was object-oriented paradigm, one would need to suck out data from model class and to project the state, construct a view class. So there starts the MVC pattern. Whereas in functional programming paradigm, a simple map operation, I'll need to have an additional step of mapping the state of the rover to the output. So here you are kind of doing it by just operating transpose and.
The data is much more immediately available to you. Of course, as Aaron said in his talk, abstractions are not something you want to avoid at all costs. There are good reasons for employing abstractions at some point. I just don't think there were really any in this case. And I think one of the things that APL allows you to do is to push that point where you need to switch to using abstractions much further off. So sometimes you need guarantees and other things.
Right. So suppose if this was a true Mars rover, then if there are many trenches or if there are rocky place and there are a lot of branching in the code that I can see in a real Mars rover, what would you be approaching? How would you be approaching?
Well, I mean, if it really was a very complex object, I might decide to use an object-oriented solution because in APL we can also do that. It's just it's not encouraged, and people try to avoid it until the last possible moment.
I think that's the important one, because I think Aaron also mentioned in his talk about when's that point when you need to introduce abstraction.
Yeah, and that depends on what kind of application you're writing and how big your data is and all sorts of things.
Yep. So I think we want to now open the floor for open reflections. Let us all reflect together if you want. What do you think you observed, and what's your take, questions, comments, suggestion on this?
Whether or not, or how easily I can see the shape of the data, or until I can actually see the shape of the data, I'll probably have I won't break through to the APL solution until I can see the shape of the data. I can probably muddle around with object-oriented programming and sort of hack my way, sort of get there eventually.
Actually, you pointed out a very big thing because that was my experience as well. When I get to see data as a whole, right? When I was pairing with Morten, right? In object-oriented solution, I could do it by parts, but I've never got the whole map of data in front of me to be able to make sense of data at once. In functional programming, you're kind of doing one element at a time. It's hard to see the big picture. So yeah, I completely agree with what you're saying, because that's what I understood. And surprisingly, I found there is this is all mathematical. You know, it helps me discover the underlying maths as well, which I could not do that efficiently in the
Well, or you get discouraged, right? The moment you move away from just having this as a matrix that you index with computed indices, and you switch to a map abstraction where, you know, you've got some system following pointers for you to find the things that you want. You're no longer thinking about the mathematical, you know, this is pi, half pi, round the circle each time. And if you think like this way, then if the rover had to turn by 45 degrees, you know, that would be a lot more simple to think about than with the abstraction sort of leads you away from the fundamental nature of the problem.
Yeah, we had.
APL stands for Abstraction Prevention Language.
No, it stands for a programming language. It's probably the worst named language in the world today, but you have to remember when it was invented around 1960, programming languages were being invented. It was invented by a mathematics professor who wanted to use it to describe mathematical operations. So he chose the name very carefully, and within his domain it made perfect sense. It doesn't make a lot of sense in this room, but it did when he thought of it.
So I think we are out of time already, but yeah, sorry.
So one of the things, like when I'm working on the closure REPL, for example, I kind of and we tend to follow this similar workflow. Like you play with the data, you see what the shape of the data is. You try to model the you figure out the shape of the data, try to model the function to what the data transformation is supposed to be. But there is simply no way to express, like, the whole value in this case is the matrix, and there's simply no way to express that in closure. I mean, I'll have to do a vector of vectors or something.
Yes, and that's exactly, yeah.
Yeah.
Then you have to do a lot of marshalling, like transform this and transform that.
Yeah.
So can I say something here? So this is exactly what I'm saying is working in the plane of the problem. This helps you kind of look at the problem here from this level. So that's all. I would yeah.
So I might discover this pattern, but I will not be able to express it like as directly as you can.
Yeah, and you know, many languages are trying to lead you away from this, right? They, you know, you're taught to use abstractions. Why would you want a matrix? I mean, why would your programming language implement a matrix? It's a stupid idea to just play unlimited games with matrices, right? Aaron.
The rover code. Along with that, I'd like to point out a syntactic element of this piece in the code. So there's a concept in the APL community called semantic density, and that's the amount of words in your code that are directly part of the domain vocabulary versus the programmer vocabulary. So if you look at a problem like this, most of those words, maybe directions or things.
Maybe I didn't pick them very well.
Right, especially, but almost all of these words you can imagine are from the problem description or from the problem domain, not intermediate vocabulary for the problem space. And the density with which you're talking about ideas in your problem space is higher here, and that's an important concept.
Well, I think there's no code here which is not directly related to solving the problem, other than perhaps deconstructing the...
But the word specifically, I'm talking about the variable name, and this is what I mean by being able to pick good names.
Yeah.
Because now all of your names are related to the problem space, rather than being intermediate issues.
It's like a DSL. It's like a domain specific language.
It's a general purpose DSL.
So yeah, anybody else or yeah.
But I would still think that, in a functional or an object-oriented approach, you can think in English. I mean, you're not looking at the structure, but you're looking at what each of those are going to do, and you try to, put them together to come up with a result. Here we are, I don't know. This is completely.
It is a bit it's a bit non-verbal.
Exactly.
It's maybe more left brain.
I never did
It's
matrix multiplication.
it's one of the One of the biggest challenges we face trying to spread the word about APL is people, we've had that question in the previous sessions, well, how do you learn to think in APL? And the problem is it's very difficult to find words in English, maybe in Sanskrit, I don't know. But in English it's very hard to find words to describe that because the English language doesn't map nicely to these.
I disagree.
Oh, okay.
Can I rant on that?
I don't know what the rules are. We
Unless-
have Naresh in the room, so.
Two more minutes. Okay. Anybody else with a question or nobody?
Okay, then I'll rant. All right. So, what you actually find, so the studies that and Payne and Miller, and what they find is that the English words that you use in your programming language are almost universally inappropriate relative to how people naturally use those words. So then, for instance, is a classic example. When people describe programs in natural language, the word then is almost always equivalent to the semicolon in C. It's never used as if then else clause, but it's almost universally used in programming languages as an if then else clause. And so the English language tends to be very misappropriated in other languages where you think it's applied. Now, APL has the opposite. The symbols don't necessarily have a nice name that you can say, oh, okay, but the structure that appears when you work with APL code and an experienced APL programmer, the structure that they create and the overall frame of the problem maps very nicely to the way people describe natural programming.
Right, I mean, but I was talking about describing the process, and perhaps this is exactly the problem as well. How do you think in APL? Well, just like you would think about anything. What are you asking me to describe? Just write the computations. This is the definition, the mathematical definition of how to compute where the rover went. Just write it.
All right. So okay.
That will unplug you guys.
Yes. Yes. So that's it. So we had other melodies which you can actually look. We had a problem of parsing which we wanted to show you, functionally as well as in APL. But you can always go to program Code Jugalbandi GitHub paradigms, and then in there are melodies. So the third one is called macro versus micro. So you can just go check.
You stole some of the names from Aaron.
From Aaron, yes. It was most appropriate in lack of words that we had, more expressive. Yeah. Thank you.
Okay.
Thank you.
Very much.